So today we're going to continue talking about solving multi-step equations, but we're going to begin looking at equations that have variables on both sides. So just a kind of reminder of what we talked about yesterday in the steps to solving multi-step equations. This should really say variables on both sides. Not sure what happened there. And when we're solving equations, we still want to follow these rules. So first, we will clear any parentheses if we have them. Second, we will combine like terms. Okay, like terms that are on the same side of the equal sign. Third, and this is really our focus for today, is we'll collect the variables to one side. The variable term to one side. And then we can solve. Okay, add, subtract, multiply, divide, use inverse operations. So if we look at this first example, there's no parentheses to clear, so we're good there. There are no like terms that are living on the same side of the equal sign. So like, yeah, there's two x's and yeah, there's two constant terms, but this equal sign is like a wall. So I can't combine things that are in totally different rooms, right? Totally opposite sides of the equal sign. So I don't have like terms that are on the same side of the equal sign. So then I go to step 3, and the reason this is super important is we can't solve for our variable if our variable is living in a couple different locations. Okay, so it's important to get this procedure down so that in order to have a single variable term, following these steps kind of guarantee that we set ourselves up nicely for solving. So I collect variable terms to one side using inverse operations, just like when we're solving an equation regularly. So one way that I could collect variables to one side would be to say, okay, if I want to move this negative 2x, I'll add 2x, and whatever I do to one side, I need to do to the other side, okay? And the purpose of doing that would be negative 2x and positive 2x would cancel out, or give me 0 x's on this right-hand side. And it would give me 9 x's altogether, so I'll have plus 19 equals 55. So by using inverse operations, I've collected my variable term to one side. Now notice the x is only getting combined with the other x term, right? I can't combine it with 19. Also notice 19 is still there, didn't disappear, right? I just moved this term over to this side, and we can't just pick it up and move it. We need to go through that procedure of using inverse operations to move 2x from the right-hand side to the left-hand side of that equation. Now that I have my variable term in one spot, now I can isolate my variable same way that we have been. So first subtracting 19. So that's going to give me 9x equals 36. And then dividing by 9 gives me x equals 4. And just like before, we can go back, we could check it. Good idea to check things when you have variables in a whole bunch of spots. So if I went back and I checked 4, then that would mean I'd have 7 times 4 plus 19 equals negative 2 times 4, I totally ran out of space, plus 55. 7 times 4 gives me 28 plus 19. Negative 2 times 4 gives me negative 8 plus 55. And then adding together 28 and 19 is going to give me 47. And 55 take away 8 is also going to give me 47. And so again, I know that that's the correct answer because I've got this balance. It gave me the same numerical value on both sides of the equal sign. When I substitute in 4, it's an equivalent equation. Okay, I have 47 on one side and 47 on the other. Okay, again, you don't have to do this check, but it's nice to do, especially if you're unsure of the final answer that you got. Okay, so now let's look at a couple together, and then I'll let you try a couple on your own. So I'm going to kind of go down the left-hand side, and I'll let you do the right-hand side on your own. Again, I don't have parentheses on this example, and I don't have like terms that are on the same side. So first thing I'm going to do is get those variables to one side of the equation. Now, up above, I could have also subtracted 7x. Okay, it doesn't matter. I tend to want to keep the coefficient positive. So like here, I would probably lean towards adding 3x. But you absolutely could subtract 6x from both sides. As long as you're doing the inverse of what's there and you're eliminating the variable term on one side, doesn't matter, you'll get to the same end spot, same final answer. So I'm going to choose to add 3x to both sides. That would give me 9 x's on the left-hand side, and I'd still have plus 22 equals. And on the right-hand side, negative 3x and positive 3x would cancel, and I would only be left with positive 31. Now I'm just solving, so I subtract 22, and I get 9x equals 9. And to solve for x, I divide by 9, and I get x equals 1. On problem number 3, now we are going to end up using all of our steps that we've written down to solve multi-step equations. So step 1, clear the parentheses. So I'm going to clear the parentheses by distributing. That's going to make this 10x plus 15 minus 4x equals 8x plus 27. So let's just go back through what I did here. I distributed 5 only to the terms inside the parentheses. So 5 times 2x gave me 10x. 5 times 3 gives me 15. The negative 4x here was not a part of that distributing, so it's just still negative 4x. Okay, now step 2, combine like terms. So I have 10x and negative 4x. Combining those like terms leaves me with 6x plus 15 equals 8x plus 27. Okay, step 3 is to get my variable term to one side. So here I could kind of go either way. I could subtract 6x, that's going to leave me with a positive x value, or I could subtract 8x, which it's nice to have x over on this left-hand side. Let's subtract 6x just because I haven't moved the left-hand side variable over to the right-hand side. Okay, so as long as I'm doing the inverse so that x's cancel out somewhere, okay, so our x cancels out now on that left-hand side, I'm good. 8 take away 6 is going to leave us with 2x over here plus 27. And now continuing to solve, subtract 27 from both sides. And that's going to give me, and I'm going to flip the equation around at this point. So I know that on one side, I'm going to have, what, negative 12. And on the other side, I'm going to have 2x. Okay, so it doesn't matter if I write negative 12 equals 2x or if I write 2x equals negative 12. Okay, I'm just kind of flip-flopping my sides as I rewrite this. So, or not, sorry, I'm saying negative 2x, it's positive 2x. Okay, so I have 2x equals, and 15 take away 27 is going to give us negative 12. And then to solve for x, we divide by 2 on both sides, and I'd be left with x equals negative 6. Okay. Let's do one more example together, and then I'll give you some time to work on the other 3. So on this one, first step again, clear parentheses. In this case, we have parentheses in more than one location. So anywhere I have parentheses, I want to clear them. So I'm going to go ahead and distribute here, and I'm going to distribute there. Distributing through 6 on the left-hand side is going to give me 18x plus 30 equals, okay. Distributing the 2 through is going to give me 20. These should be the same variable. So let's say 20x plus 20. That's just a typo on my part. And now I want to collect my variable to one side. This time I'll subtract 20x. So notice I skipped over that second step, which was combine like terms. That's just because I didn't have any like terms. Okay, so I cleared my parentheses, no like terms. Okay, let's get my variable to one side. 18 take away 20 is going to leave me with negative 2x. plus 30 equals, variables would cancel on this side, leaves me with 20. And now I'm just solving, so I subtract 30, and I get negative 2x equals negative 10, and I just divide by negative 2, and I get x equals 5. And again, for any of these, we could go back and check them and see, make sure that it works. So now I'm going to give you a chance to try 2, 4, and 6, and then start the video back up and check your work. Okay, so now you can check your work on 2, 4, and 6. 2 is a pretty straightforward one. 6 and 4, also pretty straightforward, but the answers were a little funky, so hopefully that didn't throw you off too much. 4, you get 95/15ths, which 15 doesn't go into 95 evenly, and it's not going to give you like a nice pretty integer value, but we do want to reduce that down to 19/3, and so I'm just reducing by 5 there. On 6, distributing first, a little bit tricky. Make sure we hold on to that negative sign all the way through, and then our final answer ends up being -4/3, and we can't reduce that. Don't write answers as mixed numbers. When we get to things like systems of equations and further along, having a mixed number isn't super helpful. So if it's an improper fraction, as 4 and 6 are, improper fraction meaning the numerator is greater than the denominator, then we'll leave it like that. Don't rewrite it as a mixed number. Like for example, a mixed number here would be 6 and 1/3. Don't do that. It's not going to help us later on. Leave it like this. Okay, so now we're going to look at something that happens when we start having equations that have variables on both sides, and that is that sometimes we get these special cases, which is x could have many solutions, or in fact infinitely many solutions, meaning that there's literally, I could plug in any value I wanted and the equation would still be balanced. Okay, so that's one special case that could happen. Another special case that could happen is no solution. And so no solution means that there's no possible x value that I can substitute into this equation that will make it work. Okay, it's impossible. And so we're going to look at a couple examples of what this looks like and how that feels when we're solving. So first example, again, when we're just solving, so we never know when we're going to come up on one of these special cases. So first thing, okay, I always clear the parentheses. So I'm going to clear my parentheses. That gives me 3x plus 6 equals 3x plus 6. I don't have like terms that I can combine. I'm going to get my variable to one side. Oh, okay. Well, if I subtract 3x, because that's the inverse of positive 3x, wait a minute. I canceled my variable on both sides, right? And that leaves me with 6 equals 6. Okay, when this happens, when all of my variable terms cancel out, so notice right here, all of the variable terms cancel, and I'm left with something that is a true statement. So 6 equals 6, it will always equal 6. Okay, when that happens, okay, this is the situation I'm left with, then there's infinitely many solutions. Okay, so you don't want to just leave it, walk away from the equation, leaving 6 equals 6. We want to respond in some way, and so in that way that we're responding is we're saying, oh, well, in this case, it's a special case, and there are infinitely many solutions. That means that I could literally plug anything in here, and because it's the same thing on this side as it is on this side, it's always going to balance out. So if I plug in 1, then this would become 9, and this side would also be 9. If I plugged in 2, then this side would become 12, and this side would still be 12. So no matter what I plug in there, positive, negative, 0, fraction, whatever we're going to substitute in for x, it's always going to work out that it's equivalent on both sides. There's infinitely many possible solutions for this equation, okay? The other special case that we will encounter, so first, again, clearing my parentheses, 2x plus 8 equals 2x minus 6. There's no like terms that I can combine. Collecting my variables to one side, again, whoa, look at that. All my variables are gone, right? So 2x gone here, 2x is gone there. Okay, so again, all the variable terms cancel. Okay, all, both sides of the equation, not just like, oh, and one side it disappeared. If there's an x anywhere that remains, not a special case. And sometimes that happens, like there's a funky answer, and you don't know why your answer's kind of this weird fraction or weird decimal, and you just write no solution or infinitely many solutions. It's not a special case if you still have a variable term left. Okay, if I'm solving and all my variables cancel, I either have this case, which is infinitely many solutions, or what happened here is all my variables canceled and I'm left with something that's false. Okay, so 8 does not equal -6. It never has and it never will. And if I think about that balance beam, okay, then, oh, 8's gonna way down. It's gonna be maybe heavier than -6 or however you wanna visualize what's happening there, but that's not balanced. Okay, I have 8 on one side and I have -6 on the other. Okay, it doesn't balance out. Then this is a no solution, meaning there's no value that I can plug in and multiply by 2 on one side and then add 8. And on the other side, also multiply by 2, but then subtract 6 and get the same answer. Okay, nothing is going to work for this particular equation. This is a no solution. So again, just like the other one, we've got to respond in some way. So, okay, this weird special thing happened. Don't just leave it here. We got to respond with no solution as our answer. Okay, so now on the next page, you'll find that there's 2 more examples here, and I'm going to give you a moment for you to go through and decide which special case we're dealing with. Okay, so now check your work. Example number 1 gave us all of our variables canceled, true statement. Special case is infinitely many solutions. Example number 2, my variables all canceled, gave me a false statement, would be no solution. Okay, so before we're done for today, I threw in just some more complicated problems. So something to give us a little bit of a challenge before we do some homework tomorrow with these multi-step equations. So on this first example, last class we talked about multiplying by the reciprocal. That's probably not the route I would go here for a few reasons. Number 1, I can see that if I distribute this through, it's going to be okay because I can divide 12 by 4 and I can divide 16 by 4 evenly. So it's actually just going to be fine if I distribute through. The other reason I wouldn't multiply by the reciprocal is there's a little bit more going on here. So if you remember, I said like be super careful with the reciprocal because it's only going to work for specific types of equations. So if I multiplied by the reciprocal here, which would be 4 over 1, it would get rid of this and leave me with my parenthesis. But on this side, I'd have to be careful to multiply both the 10 and the -3 by that reciprocal. And I've just found that students, this is kind of something we're going to talk about next lesson anyway, which is clearing fractions. But if there's just one fraction, I can see it's going to distribute through just fine. I'm not going to worry about kind of the intricate things that would happen if I were to multiply by the reciprocal, because students tend to make errors on a setup like this if they did that. So instead, I'm going to be okay. Okay, it's okay that I'm distributing a fraction because 1/4 of 12, or 12 divided by 4, is just going to give me 3x. And 1/4 of 16, or 16 divided by 4, is going to leave me with 4. Okay, so it's fine that I had to distribute a fraction. Sometimes it just works out nicely, right? On the right-hand side, we have, again, we can't do this, right? We can't combine these. First, we need to clear the parentheses, so the 10 is still there. Clearing parentheses gives us -3x, and a negative times a negative gives me +6. Okay, so step 1, I distributed. Step 2, combine like terms. So on this one, my like terms are constant terms. I have a 10 and a +6. So I still am going to rewrite 3x plus 4 equals, and then on this right-hand side, I have 16 subtract 3x. Okay, step 3 in solving equations, I'm going to collect my variable to one side. So I'm going to choose to add 3x. Now be super careful here. Yeah, it's 3x on both sides, but on one side it's positive 3x, and on the other side it's negative 3x. So it's not a special case. It would cancel out the variable here. These are inverses, these are opposites, but over here, I would just have 3 plus 3, or 6x plus 4 equals 16. And now we're okay, right? Now we're in two-step equation mode. So I subtract 4, and I get 6x equals 12, and I divide by 6, and I get x equals 2. And again, I could go back and I could plug in x everywhere I see an x, plug in a 2, and see if I get that balanced result. So now, just to give us some practice before we're done for today, I'm going to ask you to try the next 2 examples. And then you can check your work by completing the video. Okay, so now you can kind of go through and check your work for these 2 examples. Few places that it got tricky. On A, right away, check signs here. Then we combine like terms. I chose to subtract 3y from both sides. So one thing you'll notice is that now that we have variables on both sides, sometimes your work may look a little different than mine, but you're getting the same answer. So like if you chose to subtract 5y from both sides, that's fine. We should have landed in the same place. It all kind of works out in the end. Okay, I'm just choosing one of these variable terms to collect to one side. Okay, so again, if yours looks a little different right around here, that's cool, as long as we both landed in the same place. B is definitely tricky. So first, also tricky here is that you're not distributing 6y, by the way, right? This is like 6y minus 1, and I'm just distributing that negative, or that negative 1 through. B, so could be some sign errors here, so check your work there. And then it's not a special case. It feels a little bit like a special case up above, but again, on this side it's a positive, and on this side it's a negative. So when we go to collect our variables to one side, I ended up with positive 40 here. And then add 10, divide by 40, and reduce that fraction down to 9/4. And again, leave those in proper fractions. Don't rewrite them as a mixed number. So tomorrow you'll get, again, more practice with these multi-step equations. In the next lesson, we're going to start looking at some really tricky things with fractions and decimals.